Okay. Okay. Good morning, everyone. Thank you for spending your early Monday morning with us. We're going to share some information on offshore site investigation. We are still waiting for many people, but we cannot wait anymore, just to be fair for those who are early. So today we are going to talk about the introduction to offshore site investigation. Is an industry where I've been in the last 21 years. Next slide, please. Okay, and the plan for this presentation is we are going to go through introduction and then field life cycle. Why do we perform offshore site investigation? And then the different offshore site investigation equipment and the way we do site investigation. And in this case, we are going to talk about geophysical and geotechnical acquisition, reporting, what kind of equipment we use, how we set up, and finally how we handle the data from the raw data until we issue the report and the findings. And finally, there will be we will cover a bit on how can you get your breakthrough in your career and what you are going to prepare or you need to focus on. Especially, I will be talking in the context of offshore site investigation, of course, not all other jobs. Next, this is just to introduce myself. I'm Uzani Bashir. I'm offshore geohazard specialist. I'm Algerian and had my first degree and master in Algeria and a PhD from here, University of Malaya, Malaysia. Like I mentioned before, I was in this industry I started in this industry 21 years ago. I'm still in it, of course, doing different things, but I'm lucky to have gone from and covered all the scope of this offshore site investigation, which from let's say bidding stage, and after you win, how you prepare for mobilization, how you run the job, how you manage the job, and deliver the result to the client. So I did a lot of jobs on geohazard assessment for drilling locations, pipelines, platforms, and even associated activities like anchoring. And we have performed many projects in Malaysia, Indonesia, Vietnam, basically Southeast Asia, some in the Middle East, India, and Russia. Okay, next. Just as an introduction, so the offshore site investigation is born half a century ago, and it has helped in reducing or at least making the offshore site offshore jobs like drilling or installation safer. So they make it. It has helped to make the industry safe from the time we do exploration until we deliver the hydrocarbon to shore or for utilization or processing and utilization. The next one is, so here is the field life cycle. So any field, so the first two parts, which is desktop study and geodesy, is done mainly at the early stage of the field life, where basically they need to assess if there is what is the potential of this field for hydrocarbon recovery. So the first step in any life cycle would be the exploration. And during this exploration, we have all what is now highlighted in red here is the jobs that are done. So start with the desktop study, geodesy, just to define the corners of the block just to verify and get the corners of the block. And then they do hydrography survey, mainly is bathymetry, to make sure that the access, because some areas, although let's say we know it's 80 meters worth of depth, but then some areas could be just like as shallow as 10 meters. So we need to do this hydrography survey, mainly to assure that the navigation is possible, can be safe. Of course, then only they can run, once they are sure that the vessel will not be grounded, then they run these 3D seismic surveys and 2D seismic surveys. Then only once they have 3D, 2D means they can do their assessment, which is to define targets where they are going to drill. It means where the potential of finding oil or gas will be. Once they define those targets, then only we run this the 2D high resolution seismic for drilling. And sometimes the drilling doesn't take place, let's say in the next 6 months after the site survey. So if it's more than 6 months, usually we go back and do an analog survey for just the rig, what they call rig entry. Because, for example, the site scan sonar is only some of the data of the site survey, which is like site scan sonar, is only valid for 6 months. Anything more than 6 months, you need to redo the survey. So this is the first part under exploration. And then the next, let's say after they drill the exploration wells, they found reservoirs, they struck some reserves. Then they need to develop, they need to have a plan for development. During development, we also do 2D HR seismic, analog surveys, 2D seismic for platform, pipeline, cable, and debris survey. Just this is like a clearance survey. Once they, for example, they lay a pipe, then we have another sort of survey, which is the post-lay survey, just to make sure that we, whatever intended to be done as a construction or lay the cable or pipeline is done properly at the right place, and in the same time to confirm where we have laid that pipeline or cable. During production, so after development will be the production, which is the longer period for in a field life cycle. And we do similar surveys as well. And the last part of the field life cycle will be the abandonment, where we do mainly to verify existing structures, verify before they remove them, and then they do debris survey after they cut everything and remove all the structures. So the exploration phase takes up to 5 years, 3 to 5 years. Development could be up to 3 years. Production will be, I mean, talking about the old fields, it could be up to 20, 30 years. And the abandonment takes 2 to 3 years. It depends on how cramped is the field. Do you have a lot of infrastructure or not? And how much work you need to do to clear the field. Next. Okay, so now we want to do all this offshore site investigation, but actually why we are doing it? The main reason is because, one of the reasons is because we are dealing, the rig which you see on the third picture on your right side is actually the one. This is a drilling rig, and this is a moving structure. So you imagine if you take like this all big structures that we know worldwide, it takes a lot of effort and studies to build it and to make sure that it's stable. But the rig actually moves. So when you want to move such a big structure, you definitely need to look at the stability. So you need to study the soil conditions and other factors that are affecting the rig. Okay, this is one of the reasons. The second reason is, which is very next. Yeah, yeah. The second reason is, which is the most dangerous, especially for offshore rigs, is what you see here is a gas blowout. On the top is a jackup rig, which because of gas has totally is totally gone, and at the bottom right is a semi-sub, which actually managed to move away from the gas blowout and to a safer place. But even here, if the fire for any reason the fire starts, the whole thing will be burnt. Okay, next. Some of the issues, if you see on the left side, more. Next. Yeah, this picture shows a pipeline which is at the bottom, laid across a shipwreck. Oh, sorry, there's a shipwreck, and on the right side we have punched through. In this case, as you see in the cartoon, one of the legs actually penetrate faster than the other one, and this has caused the legs to bend. And the bending, you can see it on the top feature, top picture of your side scan sonar, which is this is the leg, and the white shadow we see is actually the shadow of the rig leg, and it shows it is bent. So this is one of the results of punch through. Next. Okay. Now I just want to list down the equipment we use for offshore site investigation, which is geophysical and geotechnical. The geophysical is, as you can read, single beam echo sounder measures the water depth, accurate water depth, but just with one beam. Multi-beam, as the name, oh my God, this one should be multi-beam. The second one should be multi-beam echo sounder, and this one, the number of beams can be up to from 101, the old systems, to 500 for the new systems. Then we have side scan sonar, which is just scanning the seabed. Magnetometer is very reacts a lot with metal items that are like pipelines. Sub-bottom profiler will give us the geological profile, but within the first 50 meters. 2D high resolution seismic gives us data up to 2 to 3 kilometers below the seabed. And drop core is just one of the items to ground truth what we see on the seabed. The sediment, the seabed sediments. For geotechnical, usually there's drilling and sampling. We have cone penetration test, drop corer as well, piston corer, vibro corer, and box corer. Next, we're going to talk about the next slide. Only the geophysical equipment, which is listed here. Next slide. And the one which is in blue are all systems which use sound to capture raw data. But if they are all related to sound, how do we get, let's say, measure only the water depth, or scan the seabed, or see the shallow geology or the deeper geology? How do we handle that? So basically, they all use sound. Next slide, please. They all use sound, but the most important is the frequency. So we tune the frequency. Next is right. Okay. So we tune the frequency. As you can see, for the side scale sonar, the frequency can go from 100 to 1,200 kilohertz. The multi-beam is from 12 to 220 kilohertz. The pinger you see here, the frequency is 1 to 7 kilohertz. Boomer is slightly lower, 1 to 5 kilohertz. The 2D high resolution seismic then is only 150 to 200 hertz, and it can go to 1.5 to 3 kilometer. And if we look at the 3D seismic or exploration seismic, 2D seismic, the frequency, the sound frequency that we use is only between 40 to 80, and it can travel up to 8 kilometers below the seabed. So the real difference only is in frequency between the different systems. Now we are going to go through the different systems just to show you what are the components, the real components of these. And this is important. Of course, if we are talking, we're talking about geophysicists only. All this, what you see here, is actually handled by a surveyor. So surveyor need to prepare the positioning and navigation system, and they connect and calibrate. So this is done actually by a surveyor. But as a geophysicist, as an engineer or geologist, you still need to know about this. And this is something I want to discuss later further later when we talk about the skills. So this is the basic positioning system, and it's always the first item to be installed on board a vessel. And the next one, then we install single beam echo sounder, which is just what you see in the box at the bottom. The rest is still the positioning system. So the positioning system is the main how call this system, where all the other systems will be connected. Okay, and in this case, the echo sounder will be connected to the navigation system. And you can see the single beam echo sounder has two different frequencies. It could be 12 and 200, or 33 and 200, which is the high frequency and low frequency transducers. Okay, next. Next. Oh, wait. Oh, next is the before that. Wait. No. Later. Oh, okay. This is a typical single beam echo sounder record, where you have the seabed as a dark line, and in the middle here we have like a possible gas seepage. But the most important is all this for single beam echo sounder record. We know the water depth. That's the horizontal scale. The vertical scale actually shows the distance, and we have coordinates. The line on top is the wiggly line on top is the vessel movement. The dark line now is the actual seabed, and we have different scales for horizontal and vertical scale. You can see on the bottom left of the display. Okay. Next slide. Again, the positioning system is still there, but for multi-beam microsounder, we add MRU, which is the motion sensor, is motion reference unit, which it will record the vessel movement. It will record the vessel movement during the survey. So when it goes up or down, it's not going to affect the value of the water depth that we are measuring. It should be, so it will refer, for example, to the main sea level, and any changes because of the vessel movement will be captured by this MRU and will be subcontracted from the sounding. One of the critical item also for multi-beam, and actually since we are measuring, everything is a sound propagation, so we need to know the sound velocity profile. So at the start of any project, we actually take SVP, sound velocity profile, which we input into the multi-beam system setting to calculate the water depth. Basically, the water depth is calculated as the signal going from the transducer, reach the seabed, come back. So we know the speed of sound in water, and we know is the distance. So we can calculate the time and the speed. We can calculate the distance, or what they call as water depth. And this can be, of course, corrected with this vessel movement. The next, this is the kind of image you can get from the multi-beam. What you see here is all actually is sounding, but then because they are so close to each other, we can grid the sounding and become like a picture. And this is what you can see here. But the original data points here are all water depth measured from the transducer to the bottom of the sea or seabed. Next. Okay. Next one is the side-scan sonar. So we still have the positioning system, and we add this USBL system with the beacons, and on the lower side where it's shaded a bit, you have a side-scan sonar fish, and then this side, the side-scan sonar fish and the winch will be, so the fish will be in the water, towed by the winch, and then the winch is connected to a top side, which will is basically the receiver, and send it to the recording system. The recording system could be there are many softwares like SonarWiz, Coda, or some are just related to the same side-scan sonar manufacturer. And in the recording system, in the side-scan sonar recording system, so it receives the data from the fish, and it merges the data from the navigation. So we know exactly each picture that we take or each scan we take will be associated with the navigation, so we know where it is. And this is very, very important. Next. This is some side-scan sonar images which show pipelines. Most of them are pipelines through different setting. If you look, there are scales, and these are related to the navigation that we receive, vertical and horizontal scale. It all depends on the navigation that we receive from the positioning and navigation system during the survey. Next, magnetometer is the part you can see at the bottom again, and it's the system is a fish we tow and then it sends the data to recording system, which is merged with the navigation to give us the accurate data and location of the anomalies, for example. The next one will be sub-bottom profiler, and sub-bottom profiler will give us the images of the shallow geology, and we have sub-bottom profiler like this one is usually is hull mounted, is a 4x4, or this is 3x3 transducer, geoacoustic transducer, which sends the signal and is received by this transceiver before it's recorded together with the navigation in a recording system. And the data we receive is next. This is the data, which is on the top is the seabed, and then you have all the layers. And if you look at the middle here, you have a sort of channel. So these are the features that we are looking for. And channel, for example, is a very dangerous feature for rig entry, because the leg, for example, if you have a rig leg here, it will penetrate more than the rig leg here. So when you have that kind of differential penetration, it causes issues to the rig, stability, I mean. The 2D high resolution seismic is the biggest system we have to mobilize. So this is the streamer. On the lower left side is the streamer. The streamer usually is like 1,200 meters long. Together with streamer, we have guns, air guns, which are filled with compressed air, from the compressor. Then the compressor and guns are connected to a control system together with other items, like other systems like the birds, which control the depth of the streamer. And all this is then channeled to the recording system, which again receive the triggers from the navigation system. So because the gun need to fire, so the compressor will fill up the guns will fire, and then the streamer will record the return from the seabed and below of the geology. And this is all related to the navigation trigger. It means let's say we trigger every 12.5 meters. So every 12.5 meter, the guns will fire and the streamer will record the signal. And at the end, at the end, we get the next. This is the image we built from 2D high resolution seismic. On the top here is the main event. Here is the seabed, because we go from water to the seabed. So the seabed looks very, very high. And then after that is, let's say, all this could be just clay and with some sand at the bottom. But the high amplitude you see here are those of interest for our study, which is this could be shallow gas. So we need to map. One of the criteria to see shallow gas is of the high amplitude. We have phase reversal, and you have acoustic masking, as you can see in the middle here, and plus other criteria. But here we can see these labels. On the left side, you can see some faults. On the left side of the image, you can see some faults. So in general, we can, from 2D seismic, we can map the geology, shallow gas, faults, channels, and these are the geohazard, if you want, or the features we want to capture from 2D seismic data. Okay, next. let's say now the client call us and they want to drill at this location, which is within this grid you see on the left side, and the middle there is a proposed location. This is where they want to drill. So the client will give us the grid, or rather just the corner of the grid, and the coordinates of the drilling location. And we will have to prepare all the equipment to do a geophysical site survey. And this equipment then is the same, just what we talked just now. We have a positioning and navigation, gyro compass, USB air, single beam, multi-beam, side scan sonar, sub-bottom, magnetometer, 2D high-res, and soil sampling equipment, which is in this case drop core. All this equipment, then what are we hoping to get at the end after we survey, do interpretation and reporting? We will have accurate water depth. We will define all the seabed obstruction to enter this grid to drill. We will check if there's any hard grounds, any scouring, what will be the anchoring conditions in this area, and shallow hazard like drilling through in the shallow geology or shallow hazard. For example, we have gas, we have faults. It could be buried coral. All these are items or features we need to map from shallow hazard. And then the drilling hazard. Now, if we drill at this location, is it safe or not to drill? Are there any features that are too dangerous? For example, is there any shallow gas there? If there's shallow gas, of course, we cannot drill because it will cause blowout, and just like what we have seen in the pictures earlier. Next, so once we know the scope of work, then we have to choose a geophysical platform. Right now, I mean, the survey vessel since the 70s was used up to today. But in 2000, we have these AUVs, which is basically a smaller version of the vessel, but this one can go to, like the one you see here, can go to up to 3,000 meters water depth, which is the AUV, autonomous underwater vehicle. In around 2010, you have this USVs, which is unmanned surface vehicles. Again, we can put all kind of survey equipment on this one, and then it has the positioning and navigation, everything. But there's no requirement for people to be on board. And the latest one, which started around 2015, are actually UAVs, is unmanned air vehicles, aerial vehicles. We are just going to go through this one by one. So for next, for geophysical survey vessel, this is the whole vessel, and then we have all the equipment. If you look, there's a compressor, there's an air bank, streamer, winches for side scan sonar, and on the bottom part you can see side pole for USBL and echo sounder, and for multi-beam echo sounder pole as well. So this is how we mobilize all the equipment into the survey vessel. Next. And once all the equipment is surveyed, then we actually tow and pull all this equipment running in same time. That's what they call single pass survey. Single pass geophysical survey. As you can see from the boat, there is this the closest one is the seismic source, and behind it is the streamer. So the seismic source will as we talked just now, will send a pulse, and it's reflected from the seabed, and the below layers and captured by the streamer. For sub-bottom profiler, as you can see here, is the yellow fish here. This can be towed, but we can have it also inside the hull mounted or inside the vessel. The multi-beam is, in this case, is hull mounted, but like I showed in the previous image, it can be on a side pole. The side scan sonar is towed, and usually the side scan sonar will be towed like 3 times the water depth. This is some convention for this one, and we can piggyback the magnetometer to the side scan sonar, so we can tow both in same time, and there is no interference in both between these two systems. And all these are recording while the vessel is sailing. On top of the vessel, you can see the Starfix is the actual positioning system, and the positioning and navigation system are all on board. And if we want to take samples, you can see the drop core here. But in that case, once we finish the geophysical acquisition, then only we recover everything, and we can do the drop core. We can run the drop cores. Okay, next. This is just so we have when we go to deeper water. Usually we use this kind of vehicle, which is autonomous underwater vehicle. Like this one is a Huygens 3000. It's quite big system, but it's autonomous. It's like you load the job to be done, like the grid we have seen just now. Load the grid, ask them which sensors they are going to use, and then launch. It will go and work 20 to 25 hours before it's retrieved to download the data. So it does all the work on its own. The one you see here used to be in Malaysia, but it's no more here anymore. It's taken over by a different company. And this system can be fitted with the same multi-beam, side scan sonar, sub-bottom profiler, some parts. So they have the magnetometer, they have a camera, and all the sensors to measure for example, the sound and everything. This is 4.9 meter long, 0.75 meter in diameter, and can move from 1 to 6 knots. Okay, the speed. Next is a smaller AUV, which is only 3 meters long, 0.3 in diameter. It can still move 1 to 6 knots. Unlike the Huygens, which spend around 20 hours to 24 hours in the water, this one only can maximum 8 hours in the water, and can dive only to 1,000 meters. And like the Huygens, which can go up to 3,000 meters. Okay. The next one is the latest technology, which is the UAV. We use drones to actually do hydrographic survey. For example, in this case, you can see in the photos, you can see the drone going down until it's actually carrying the side scan sonar, and you can go inside the water, and after that just follow a grid to survey let's say for this lake. The grid can be automatically loaded into the drone, and it will be set, for example, to fly 1 meter above the sea surface and fly along the grid. And the data can be, as you can see at the bottom here, it can be displayed directly on the laptop, or after the drone comes back, you can download the data as well. Okay. The last, oh my God. The last is a USB. Again, it's the MN system which carries the same survey equipment. Okay. So now that we have collected all the raw data, next USB. Yeah, USB. Genau. Genau. Okay. It's okay. Yeah. So now that we have collected the data, next. Yeah. Now we have collected data. What data we collected? Position and navigation, single beam, multi beam, side-scan sonar, 2D high res, and so once we have the raw data, then our next work, especially for the geophysicist, geologist, and surveyor, is to convert all the raw data into charts. And this is the list of charts that we make for every site survey. And the next item will be how to convert these charts and drawings, extract the most important features from charts and drawings and come out with a report, which will include, let's say, accurate water depths, slope gradient, seabed morphology, what kind of hazardous features are on the seabed, on the shallow geology and the intermediate geology. When say shallow geology is up to 50 meters. Intermediate is the most important part, is up to 1,000 meters below seabed. And then, of course, with all what we have, then we analyze what is the rig entry. Is it safe or not? Once we enter, is the way to enter to the site, is it safe or not? And then rig emplacement is once we are at site, we try to jack up the rig to enter the soil. Is it safe or not? Once the rig is emplaced, it's safe, then we start drilling. Then that's where we check the drilling conditions. And before that, we check also the anchoring conditions. So from the raw data, we answer all these questions, which are our findings that are useful for the client to take decisions what to do next. Okay? Geophysical, oh my God. Next. Wait. Go back. Okay. I'm open for questions if you have anything to ask. You can just on your microphone and ask. Hello? No, can. Anyone has any question on because we finished the geophysical part. No, what happened? Hello, you just can open your microphone and ask question if you have. If you don't have, we are going to move to the geotechnical part. No, okay. We move to the
question. So far, no question for me.
Okay. Thank you.